Hello. I started speaking Spanish for some reason. I don't know. I just started checking that sound works fine. Yeah, I think so. So, hello everybody. Welcome to Arduino's livecast number 17. This is David Cuartillas, co-founder of Arduino, and it is May 30th, 2018. And today we're here to talk about Arduino basics. This is one of the eCraft to Learn livecasts, and we're doing them within the context of the eCraft to Learn European Research Project, and we're trying to bring basic topics related to microcontrollers and learning so that teachers, or better say educators all over the world can use these materials in their classes, or at least to educate themselves to use them in their classes with their students. But before we start, I would like to thank very much the members of the Arduino Discord channel. As you can see, always up there on the video there is a URL, and that's the URL for the Arduino Discord channel that we use for live casting. And I'm gonna show you the chat online. This is like this, and then you can see this the live cast. Sorry, this is the Discord channel we're using for chatting. So if you're a teacher or if you're an Arduino user and you'd like to have like a quick chat about anything, you can always come here. This is actually meant to be used for the Arduino community to discuss quick issues. If you have a more in-depth kind of problem to discuss, please use the Arduino forum. So if you're like not finding a URL for something, you can always ask here, and there will be probably somebody. And I want to welcome Blue Light Show and Kaiser. I don't know how to say his nickname. These two guys from the US volunteered this week to pimp up the chat and add a bunch of bots to make it work nicely. And you can see here on the right hand side how now everything is colored, and you can see we have a decent amount of users. And as the community grows, I think we need more external moderators to make it happen. So I want to thank you guys for all the effort you're putting. And you know, if you want to be part of the chat, please just join. And we will use the chat to get any kind of questions for the livecast. And no matter how complicated or hard the livecast is, we will always try to answer the questions. And if not directly, once the livecast comes to an end, I will stay in the chat for a while, sometimes some hours, and continue to talk about whatever was discussed. So let's go back to today's program. Today's livecast is not very long, and so I will try to spice it up by bringing the very exciting tool of the multimeter. And the idea is to talk about voltages, current, resistance, and all of the basic aspects of electricity that have to do with this, basically with an Arduino board. Where do voltages go? How much voltage runs on an Arduino board, and things like this. And also look at the basic laws of electricity. And of course, these livecasts, slideshows that I typically use are prepared by people that have been into the field for a while. So not everything that might be relevant to you might show up. So that's why you should use the chat to ask any kind of question. So if you're watching this thing live on YouTube, please use the URL that shows up either up there or in the comments of the YouTube video channel of the Arduino team video channel to refer to Discord. Discord is a free app, and you can use it for chatting, and you're welcome to use it. And please remember, subscribe to the Arduino YouTube channel. So let's talk a bit more about this. So which are the basics of, it says here basics of electronics, but we're mostly going to talk about electricity today. So we're going to talk about voltage, current, resistance. We will talk about the Ohm's law. We'll talk about AC/DC, not the band, but the difference between alternating current and direct current. We'll also look at basic concepts like closed and open circuit and what is power and ground, in case you don't know yet. And again, as you know, some of these livecasts are more advanced, and some of these livecasts are a bit less advanced, and this is to be able of addressing the whole community. So I mean, it's understandable that if you're looking for a more advanced kind of livecast, today's livecast might not be for you, but you're welcome to post again any kind of suggestions for LiveCast. You know, I'm taking suggestions. Sometimes I will look for the weirdest sensor. So just use the chat to make any kind of suggestions and propose ideas. Anyway, let's talk about voltage, current, and resistance. What are those friends of ours? And here we have made the classic explanation using liquid as a way to explain what current would represent. So let's take a look at what the slide says here. It says voltage is the difference in electric potential between 2 points. And this is very hard to explain as the picture. But the idea is that the voltage will be, in a way, symbolizing the difference in the amount of electrons between one part of the space and the other part of the space. And those electrons will generate electric charge in the part of the space. And it's typically the 2 points in space will have different amounts of electric charges, so the voltage will be the difference between the electric charge, which is not the amount of electrons, but it's the, each electron represents a certain amount of charge. So if you have 10,000 million electrons, that will represent a certain amount of electrical power, and the difference in that power is the voltage. And in a way, it represents, as it says here, the possibility for that energy to be transferred from one place to the other. And if there is no voltage difference, there will be no global amount of energy be transferred between those 2 points. But this is like, you have to think about it like heat. If you have something that is really cold, like this glass of water, and something that is really hot, like my hand, if I touch it, it's not that the temperature gets immediately the same. It takes a time where there is heat transfer from my hand to the glass, and my hand gets colder as well, and at some point it will balance. But what happens also with voltage is that the electrons are never static in a place. You cannot really know where an electron is, so they keep on moving around. So we're always talking about average values in different volumes in space. So if there is a difference in potential between 2 different volumes in space, then there is a certain probability for the current of electrons to flow from one place to the other. The average, we're always talking about average current. So voltage represents the potential for this current to flow, while current, as the next slide shows, talks about the actual flow of the electrons from one place to the other. And voltage is measured in volts, as it says the slide here, so it's pretty straightforward. Well, current is measured in amperes. And while in the world of electronics, and I want to give you some dimensions, in the world of electronics, of digital electronics, voltages are kind of like easy to read. We talk about 5 volts for high in the Arduino Uno, 3.3 volts high for the Maker 1000, for example, and 0 volts for low as for the as a reference. So you see, we're talking about numbers that we can refer to easily. When we talk about current, we talk about milliamperes. So the current that for example, the Arduino Uno, an Arduino pin will release will be tops 20 milliamperes, which is really not a lot. So you can barely turn on or off an LED. So if you want to turn on and off a motor, for example, you cannot really do that from the pin of an Arduino Uno board. You need to use something else, and even less from a Maker 1000. And this, because this is like this for more or less all of the digital logic. Digital logic is not really meant to drive motors. It's just meant to do logical operations, and then you're supposed to build something in between. So you basically play, in a way, you play with voltages inside digital technology. And when you want to reach certain current to affect the physical world, you need to use something else, which we call a driver. So also these 2 slides I've been showing until now are talking about, are showing an illustration of water flowing in a pipe, and they try to signalize the idea of resistance. What is resistance? And in language, we typically say that resistance is how difficult it is for electricity to move from one place to the other through a material. So for example, if you have a piece of wood, like this table I'm having here, wood will be a lot more resistant than a piece of metal, like for example, the tip of this power plug, This is made of metal. So metal allows for electrons to flow easily, and that has to do with the very nature of the material. So you cannot really make wood to conduct electricity that easily. You need a lot of current for it to change its behavior and work in a different way, but then it will burn very quickly and it will stop working. So resistance, which is the opposition of a material to the flow of current, is measured in ohms. And again, we measure resistance in typically between hundreds of ohms to thousands of ohms. When we talk about digital technology, we don't really go much farther in the scale. Sometimes we use mega ohm resistors for building things like, for example, vibration sensors. But most of the time, we move in this range between the hundreds and the thousands of ohms for most of the applications we're going to see in digital technology. So just keep this in mind. I think having an idea of the proportion of things is important to understand how things work and eventually discover something new or something that is not really working, because you might eventually have misread the value of a component. So what this drawing is showing here, and I think this is very relevant, is a metaphor. There is different metaphors to explain how current flows, because it's kind of hard for people to understand this in terms of small tiny particles that move through materials and of which you have to make an average value to understand how they're moving. This is really abstract, and sometimes it's hard to understand. So there is a lot of different ways of abstracting the idea of electricity and how it works, and water is one of the ones that is used the most to explain something very simple, which is Ohm's law. And in this case, in this drawing, you see how water goes through this pipe, and if there is a bottleneck in the pipe, that will act as the resistance. So you cannot have more water going through the pipe unless you increase the speed at which the water is propelled. But there is always going to be a physical limit that has to do with how many particles of water can go through this bottleneck. So that's what resistance is going to signify. So as I was saying, there is a relationship between all of these three components: current, voltage, and resistance. So the Ohm's law states that the current is directly proportional to the voltage divided by the resistance in a circuit. So every circuit that you have around, like for example the circuit inside the multimeter, or the circuit inside your Arduino board there, it can be represented as a resistance. So every circuit. Eventually, you can model your circuit with some other components that I'm not talking about right now, but basically everything can be modeled as a resistance. So if you apply a voltage to it, and if you can measure the current that goes into that thing, then you can establish which is the resistance for that whole circuit. This is what Ohm's law comes to say, because there is this proportion between the amount of current going into something versus the voltage that you apply in order to get that current flow to go. That will give you the value of that resistance. And you can move this thing around. For example, when I learned Ohm's law, we talk always about voltage equals current times resistance, or like in this formula here, you can say that current equals voltage divided by resistance. At the end of the day, both formulas are exactly the same. It's just a different way of telling the story. And one thing that is very important to note, and as you see here in the drawing, the current is always drawn to go from the positive pin of the voltage to the negative pin. And in the circuit you see here, and I'm gonna mark this with my mouse, the battery, or the voltage, is given by a battery. This symbol here with a long line and a short line and a plus sign and a minus sign, that is the logical symbol for a battery in a schematic. This this kind of radiator drawing is the resistor, and this is the resistor in US terms. Because of course, why should we all have the same symbols to represent things? There is a different way of representing the resistor for European schematics. It should be a rectangle. It's just a thin, long rectangle. And the current, it does have a direction. It goes from the positive pin on the battery or the power source or the voltage to the negative pin. So this means that the current, which is an abstract concept, is always going to go that direction. But for real, what is going to be flowing is electrons, and the electrons go from the negative pin towards the positive one through the circuit. So this is very, very important because it's very confusing for people that current goes in the opposite direction to the electrons, when current for real doesn't really exist. It's actually representing kind of like the spaces between the electrons that go in that direction. That represents like a positive flow of energy the other direction, you know, because the real thing moving around is the electron. So what's the difference between AC and DC current? So alternating current, or AC, implies that the charges, which is the electrons, are moving back and forth. So this is where the water analogy breaks. You know, you cannot really easily use the water analogy to explain alternating current. You cannot. Can you see the water going like back and forth like this in a pipe, right? It doesn't really work. So what you have is the electrons that they go back and forth, and by going back and forth, what happens is that stimulating the first electron in a cable will stimulate the next one and the next one and the next one and the next one, and that will provoke a stimulation of electrons all throughout the wire to the end of the wire. And this allows actually to send current to really long distances. For the same kind of amount of nominal voltage, you can send current to a much longer distance. That's what alternating current is very useful for. Also, alternating current is what's produced by a motor. When you put a motor to spin, it's basically having a magnet, and that magnet, or a turbine, sorry, I'm saying a motor, but I actually mean a turbine. When the turbine is spinning, it generates changes in the polarity of the magnet. It generates changes in the voltage that's being stimulated on the terminals of the motor, and that generates an alternating current that you could eventually measure. So, for example, European wall sockets, they have an alternating current that goes on 230 volts, peak to peak. I think somebody made a mistake with my documentation. And it will oscillate at the rate of 50 hertz. This is different for the US, Mexico, and so on, where the voltage is actually 110 and the rate is 60 hertz. And this is relevant because then it makes different components have to be ready, or different designs to be ready to be used under different situations. On the other hand, direct current is not working in the same way. Direct current is just how we understand the current from a battery perspective, and it totally respects the water analogy that I presented earlier. So in this situation, the charges, they are moving in a single direction. Once you put it to work, the charges, which are the electrons, they go from the negative part of the battery to the positive part of the battery, following the circuit through all of the components, and they are collected again in that single place. And eventually, as it says here, batteries produce the DC current. So the difference again is that there is different components, and they will behave differently in front of different charges. For example, let's take a capacitor, which is a component we haven't explained yet, but we will eventually come in a later livecast. But a capacitor is made of the easiest capacitor is made of two plates of metal confronted like this, and there is a cable coming here that brings current, and a cable coming here that brings current. So if you get a DC current comes in, and it starts to stimulate the electrons here, and it stimulates as much as it can, but once it has taken all of the electrons from here and there is no more electrons to take, then there is no more voltage, so there is no more current that can flow from here. So in a way, a capacitor will be stopping the flow of electrons if you use direct current. But if you use alternating current, you know, the electrons are coming in and out. This will generate also electrons coming in and out in this other place. So you see, different types of current will work differently with different components, and this is also a very complex thing to explain in the first place. So it's very important that when you explain about components, you use step-by-step procedure, trying to explain why they work this way, and try to make always a relationship between potential metaphors you might be using, like we use a water metaphor, explain also when it breaks, and so on. I've read a couple of books about how to explain the metaphor of electricity at this point in my life, and there are some authors that defend that it's much better to start explaining the electrons from the beginning, maybe not at 5-year-old kids, but that is much better to actually, as soon as possible, introduce the whole idea of the electrons, because it will really help people to understand how the whole dynamic works for electronic components. Because otherwise, you have to be changing metaphor all the time, and that makes it very complicated. So it's again up to you. Personally, I use the water metaphor sometimes, a little bit, and then I very quickly jump into electrons and try to explain everything from there and build a whole narrative around that. So let's continue talking about closed and open circuits. At some point, I'm going to jump to basically measure voltages on an Arduino board, by the way, so you can see how it works. Oh, there is a question in the chat. Thanks, Damson, for asking this question. He asked, "What's the which potential versus in the ratio potential versus current? Which is the dangerous one? Which is the fundamental meaning?" Okay, when I guess when talking about potential, I guess that Damson is talking about here's the chat question. He's talking about voltage. So let's say this way: nothing is dangerous. This is like, is driving drunk dangerous? Obviously it is. Is leaking a battery dangerous? Obviously it could be. So nothing is really dangerous unless you use it the wrong way. So we always say that the dangerous thing is current, because the flow of current through your body, eventually through your chest, could provoke a heart attack. And you don't need a lot of current to do that. You need an ampere. An ampere could be enough to provoke a heart attack. And so there's a couple of rules that you should always respect when you're working with electricity. First of all, even though you're left-handed, it's recommended that when you plug in wires in a circuit, you use your right hand. Because your right hand is, if there is a discharge of a component, it will go through your hand, through your right part of your body, all the way to the ground where your feet are. So it will stop you of getting electroshocked eventually. So you should not work with both hands like this, because if there was a short circuit, it will just go through your whole body and your chest and eventually provoke a heart attack. It's very easy to feel. I mean, you can do it as like this. There is this electrical games that they sell at stores where you have to press a button faster than the other players, and the last one pressing the button gets an electroshock. Well, we dismounted one of these for playing in class with my students, and somebody was holding the both terminals, the worst part of the controller, with each one with one hand, and this person said that totally felt the current going through his chest, but luckily enough, it was like stopping after half a second, so nothing really happened. So it's very important. Current, in a way, is a dangerous thing, but of course, if you touch something that is at 25,000 volts, you might get an electroshock. So because you're closing a circuit, that's the issue. So, but for example, what happens if you see a bird sitting on a power line? The bird is not getting fried. So why is the bird not getting fried? Well, because the whole body of the bird is at the same voltage at the same time. So if your whole body is at the same voltage, there is no current flow, then nothing happens. So I guess this is what will be answering this question, Damson. So the current, the difference in voltage between different parts of your body will provoke electric current to flow, and that will eventually provoke burns and other things. So current is the most dangerous part. But still, seeing something at 20,000 volts in front of you is also kind of dangerous. So you should be kind of careful. And as I said, the reason why it's dangerous, since you keep on asking on the chat, the reason why it's dangerous is because there will be a flow of electrons through your body. Okay? Okay, so Miro says that he's having issues with the sound. Can you please confirm, everybody else, if you're hearing it properly, just to make sure? I'm pretty sure that the volume is maxing on my end, so I just don't want to also have too much sound running here. And while you confirm that, we continue talking about closed and open circuits. And so this is in a way related to the question that to the question that was asked a second ago. Let me see if people keep on asking if I can max my volume a bit more. So I'm gonna just try to. Okay, is it better now? Is it louder? I'm pushing it a little bit too much. On the other hand, I don't know if you're listening to the connection through Discord, because we have a voice connection through Discord, or you're listening to it through YouTube. Because if you're listening to it through YouTube, then I think we are maxing the sound. So it's a big difference on where the sound is coming from in this case. Okay, so what's the difference between closed and open circuit? Continue with the slideshow. So a closed circuit is the one that allows the current to flow. So when we talk about the closed circuit, we're talking about the one that lets the current go from one place to the other. And here you see an illustration that very clearly illustrates a closed circuit with a battery. Just to be clear, the drawing is a drawing of a 1.5 volt battery, which will most likely not light up the LED that is in the drawing. This is just to highlight the idea. Okay, just to highlight the idea that where is the plus part of the battery versus the negative part of the battery and so on. So we talk about the closed circuit when there is a path for the electrons to go from one place to the other. And we talk about open circuit when there is not a path for the electrons to flow. If the electrons can't flow, if the circuit is open, then the circuit will not be working. So this is very important to understand, because in a way, the concept might sound a bit weird. So closed actually means functioning, and open means not functioning. So, and this actually can be linked to this idea of voltage and current we were talking about a second ago, and the question of Damson. If you have a wire in front of you, a wire like, I have wires all over the place, but I have like no open wire. Let's say this is a wire, and let's say this wire here is coming from somewhere and is not touching the other wire in a circuit. The circuit is open, and there will be no current flow because there will be no electrons going from one part to the other of the wire. So nothing will happen in the circuit itself. It doesn't matter if the battery is connected. If you haven't turned on the switch, it's not going to work. So the switch in a way opens and closes the circuit. Opening means off, and closing means on. This is very important to keep in mind. These are very simple concepts, but it's very easy to get them wrong in the beginning. And then just to finalize like the last concept for today's video, power and ground. So what is power and ground? So the Arduino board that you see here in the slide has a bunch of different pins, and they represent connections to the chip, except for the ones that are related to power. And those that are marked with G and D, that's the acronym for ground, and that is the place where we typically end all of the circuits. Power represents the voltage that we apply to the chip, but we also make it available on the Arduino board for you to use it in building your own circuits. So this means that between the 5 volt pin and the ground pin, there is a connection that you can use to plug in your own sensors. So you don't need an external battery to power up your sensors and most of the actuators. Okay, so as I said, I have here an Arduino Uno board, and I have a multimeter, and I wanted to use this to just explain you a little bit how a multimeter works, because it's a super useful tool, and in the slideshow we have nothing about it. Actually, this is the last slide that I have for today. So the multimeter is a very useful tool that can help you measure in voltage and current, as well as resistance. But when you work with digital technology, most of the times you're never measuring current. Okay, this is very confusing for people. They think you can go measure all of the 3 things everywhere, and that's not really how you work. So when you measure in a components, you typically never measure the resistance. You definitely never measure the current. the thing you always measure is voltage to see that the voltage arrives to the place at the expected value. So I'm going to turn on the multimeter, and before I go on with that, I wanted to show you how the multimeter works. Oh, I did have a different camera. Let me see. Is the one? No. 1 second. This is the camera I wanted. No. This is the camera I wanted. No. This is the. Whoops. Looks like my second camera here. 1 second, I need to just configure this camera. Okay, no, it stopped working right now, so I will do it with this one. So this is the multimeter here. You see that there is different types of multimeters. The more expensive ones, they are completely automated. This one is mid-range, mid to mid-high range. It's pretty good. It has different areas of measurement around it. It has an area that measures direct current. This is you see voltage, and it measures direct current voltage. You can also measure direct current. This is the A with the double line on top. You can also measure alternating current. There you have it, and alternating voltage, which is this V with a tilde on top. And you can as well measure resistance. And the other thing that is important is that it's not really giving you values that are straight numbers, or a single, sorry, it's not giving you like a single number to measure. It gives you a scale. So for example, in voltage, I see here, there is values on 200 M, which is millis, 220, 200, and 1000. This means that if I want to measure direct current or direct voltage, that I know it's going to be up to 2 volts, I should go and put it on that part of the scale. If I want to measure up to 20 volts, I should go to the next point of the scale, and so on and so forth. You know, it's very important that you respect that, because otherwise the measurement is going to give you that is overloaded, and you will not read anything. So here's my Arduino board, and I know that the different pins here, some of them are ground, some of them are power. I'm going to just plug in this connector just to make easier for me to measure. So just plug it in. So I have naked pins up here where I can punch in my terminals. So as I said, you will typically measure voltage. And the reason for this is that in order to measure current, you cannot measure current just by touching here and there. You need to build a circuit where the multimeter is in the way of the current, and it's really, really hard if the whole circuit is already mounted. You cannot just cut a wire and put the multimeter in the middle of something to measure where the current is going through. That's why you're going to be always measuring voltage. Of course, if you build a system with a motor and you want to understand how much current the motor is consuming, you can always put the multimeter on the way. But it's really hard to cut a digital circuit somewhere to just put a multimeter in the way to measure where the current flows or not. So you need to focus on measuring voltages. So I guess you can read that properly. So if I touch on the ground pin and I touch on the 5 volts pin, you see how right now it's giving me a measurement of 4.48. And that is more or less 5 volts. I mean, it's not exactly 5 volts because what I'm getting is I'm getting 5 volts through the USB port, and there is some components on the way that are draining some current, and so my 5 volts pin, I'm not getting exactly the 5 volts voltage. And if I if I go down one more pin, I can connect my multimeter to the 3 volts pin. Okay, that's the 5 volts. You see, earlier I was measuring on the wrong pins, so this 4.99 is a bit more accurate. I'm going to the next one, and I get 3.28, and that's on the 3.3 volts pin on Arduino that is used to eventually power small sensors that might work at 3.3 volts. The 3.3 volts on Arduino Uno is not giving you a lot of current, so you should not really use it to power anything at 3.3 volts. You can power up small circuits like a IMU that works at 3.3 volts, for example, but not a motor. While the 5 volts being here, you can really use it to power up, for example, a small DC motor. Sorry. So let's this very much ends the LiveCast for today. So I'm just gonna take again Mido's question from the chat. So he's saying whether we can clarify once more the whole idea of open and close, and I will use that just to finish the LiveCast. And so here you have the open and close circuit. So you see here two different, and now it is especially directed to Mido since he asked in the chat. You see two different drawings. The idea of these two drawings is to exemplify the concept of open versus closed. An open circuit is a circuit where there is a place, which is a switch somewhere, could be just two wires not touching each other, so that there is no path for the electrons to go from the battery, from the negative pin of the battery, all the way back to the positive pin of the battery. So not being able of doing that is because the circuit is open at one or more places. This is a really simple circuit, but you could imagine a circuit with a lot of different places like this one that will be open. And closed means that there is at least one path for the current to flow from the negative pin of the battery to the positive pin of the battery. Sorry, the electrons, the current goes in the opposite direction. Okay. So when a circuit is working, it's because the circuit is closed. If the circuit is not working, it's because the circuit is open. And this sounds really strange when talking about open hardware, right? But it is a bit how it is. So with this, friends, I can call it a day. I presented some basic concepts on how Arduino, electricity around microcontrollers, which is electricity around Arduino boards, essentially. If you have any questions, please use the chat for small questions. Use the forum for more project-related questions that require more attention. Remember to subscribe to the Arduino YouTube channel. Remember to subscribe to the chat up there. And if you are a member of the Arduino community, very soon you're going to get an email reminding you about remaining a user with us. So please continue to be a member of the Arduino community and continue to share your experiences with us and the others. So thank you very much, and see you at the Arduino LiveCast in a week from today. Goodbye.